So in this example, we're going to find the residues at the poles of this function using two simple pole methods. Firstly, this one, part A, and this one in part A and this one in part B, to compare which is faster. So first thing to note, the reason this is a simple pole, okay, so there's obviously a singularity at z equals -1 and another singularity at z equals 1/2. Hopefully it's clear by now that these are simple poles. Okay, so 219, basically all you do is notice the z minus z naught and multiply the expression by z minus z naught, so it disappears, and then what you have left is something divided by something, which is, both of these things are not 0. So here all we do is we see the z plus 1, so we multiply by top and bottom by z plus 1 and then evaluate what we have left at z equals -1. Okay, so the residue then is substitute z equals -1 into the top, you got -1, and substitute in z equals -1 into what you have left on the bottom, and you get 2 times -1 minus 1. So the answer then is 1/3. Now to find the residue here at z equals 1/2, you have to be a little bit careful, because what you're meant to do is multiply, okay, you have to get it in the right form. So what we mean by that is that yeah, suppose we can write, to use this 219, you're saying that we need to write the function in the form p divided by z minus z naught times r. So you need to get it in that form. It needs to be z minus z naught, not 2z minus something, okay? So here we've got 2z minus 1. So we have to get it into this form of p divided by r divided by z minus z naught. So to do that, you take out a factor of 2 here. So you end up with this expression here. Then you're safe to multiply by z minus z naught. Z naught is 1/2 in this case. So once you've done that, then you're okay. You're good to go. So then you can write, substitute in z equals 1/2. You've got 1/2 divided by 2 times 1/2 plus 1, and you get the answer 1/6. Okay, so this is a bit of a hassle. You have to be careful to remember to do that, to write, this bit in terms of z minus z naught. Okay, so now we use the other method, which is really the method I recommend. Less direct than first, but the formula really isn't difficult to remember. So it's p divided by q dashed. So the important thing is that p at z0 is not 0, and q at z0 obviously has to be 0, otherwise it's not a singularity. Right, so if we do that, then, well, we're going to have q, okay, for the first one, so the singularity at z equals -1, then we choose to make q the z plus 1 bit, and the p is everything else. So q dashed is simply 1, and p is z over 2z minus 1, which we evaluate at z equals -1, so we just end up with -1 divided by -3. Yeah, 2 times -1 minus 1. Now, so really it seems pretty much the same amount of effort as the first method. But when we look at the other singularity, this is where this method is slightly better in this case. for the z equals a half, we don't have to worry about rewriting it in this form. We just use the same approach. So the q bit is this now, the 2z minus 1. Obviously, when z equals a half, that's 0. And the p is the z divided by z plus 1. So p in this case, evaluated at z equals a half, is a half divided by 3 halves. And q dashed, well, q is 2z minus 1, so q dashed is just 2. So we end up with half divided by 3 halves times 2, and we get 1/6 again. So this method is faster in this case, slightly faster. And you're less likely to make a mistake as well, because it's easy to, using the first method, it's easy to forget to put this 2 outside, and then you get the wrong answer. Now, in the next example, you'll see that the second method, p over q dash, definitely is faster. We won't bother trying to use the first method in this case. So now in this example, we want to find the residue of e to the minus az times shek z at the singular point z equals I pi by 2. Okay, just to realize why it's a singular point, remember shek z is 1 over cosh z, which okay, we've written here. And cosh z has zeros. It's sort of like cos z, but rotated 90 degrees in the complex plane. So you know that cos z has zeros at pi by 2. Therefore, cosh z will have a 0 at I times pi by 2. Okay, so we understand why we get a singularity. Again, this is a simple pole. So, how do we find the residue? Well, strongly recommend the p divided by q dash method. So this is obviously going to be our q, the cosh z, and cosh z is easy to differentiate. It's just shine. So we can just plug things in immediately. This is our p. So we put, when we got p evaluated at z equals I pi by 2, so that's what we got here. And then we've got the derivative of cosh z, which is shine z evaluated again at z equals I pi by 2. So then it's just a matter of doing the algebra. So the top bit we'll leave the same. Shine I pi by 2. Remember, shine I z is equal to I sine z, useful formula to remember. So you just get I sine pi by 2, which is just I. You might like to think why I've left the residue expression in this form. I'll tell you why at the end of the mini lecture. Okay, next example. Okay, I mean, the reason we're using this p over q dash method in this particular example, it should be fairly obvious that this expression here is obviously not in this form, p over z minus z naught times r, and it would be somewhat artificial to try and get it into that form. So this method here is completely impractical for this this example. Now in the next example, okay, we could factorize this, and we could use the first method after splitting the 1 minus z to the 4 into the 4 factors. But really, it's not worth the effort. The p over q dash method is so much quicker in this case. So obviously, this is the p. Cos of z is when z equals I. Cos of I is not 0. When z equals I, obviously this is 0. So this is the q. Differentiate the q, we get minus 4z cubed. Evaluate this at z equals I. So we've got cos I, which remember cosh iz is just, cos iz is equal to cosh z. So we just got cosh of 1 on the top. And on the bottom, well, it's minus 4i cubed, which is the same as 4i. Again, I've left the I on the bottom. So the reason is, what do we use residues for? Well, to evaluate integrals. And the residue theorem states that we want to work out things like 2 pi I times the residue, or 2 pi I times the sum of the residue. So we tend to leave the I at the bottom because it's going to cancel with the 2 pi I. That's why I've done that.